Welcome to Data Skeptic Time Series.
This is Data Skeptic Time Series, the podcast about how to predict the future based on historical sequential data. Episode number. In many software projects, there are more lines of code testing the software than actual lines of code implementing the software. This is because of the critical importance of automating the regression testing and making sure engineers can move fast and not break too many things along the way. Or at least have a test that quickly fails whenever they do break something, which is probably going to be often. Not every aspect of a complex software application is a binary deterministic test. For teams committed to high-quality continuous integration systems, more sophisticated techniques like change point detection are required to analyze software performance. Today on the show, I speak with Daly from MongoDB about change point detection and other aspects of their testing pipeline.
I'm Daly. I work for MongoDB, where I'm a performance engineer.
What does it entail being a performance engineer?
That's changed a lot over the 7 years I've been at MongoDB. Originally, we had no infrastructure, so it was a lot of flying by the seat of our pants, trying to do everything at the same time. Then turned into building a lot of infrastructure so that we could test and track the performance of MongoDB. And now, largely, I get to use those tools and teach other people about using those tools internally.
Well, I would be somewhat surprised if most of the audience wasn't already familiar with MongoDB, given how prolific it is. But just in case, could you give us a quick summary of what this technology does for people?
We're a data platform company. We sell a database called MongoDB. We sell database as a service through Atlas, and we want to make it really easy for everyone to use their data.
In terms of the build process and the software and all that, are you open source or closed source, or what's the nature of the code base?
Our source is available on GitHub. We have a small fraction of the code that's in an enterprise repo that's separate, but all of the core technology for the database is open and available.
Well, with that in mind, I guess technically I could go on and maybe find a bug or even propose a feature and send a pull request or something like that. Is there a lot of community activity on Mongo, or is it generally driven by a core dedicated team?
It's mostly driven internally, but we do accept pull requests. We love to get pull requests. It's a wonderful thing. But most of the development is done internally by the company.
So the paper I invited you on to discuss is called The Use of Change Point Detection to Identify Software Performance Regressions in a Continuous Integration System. So exciting stuff to unpack there. Maybe to get started, could we talk about that continuous integration system? How does MongoDB get built?
We've been heavy users of continuous integration for a long time. So we build and test MongoDB in a continuous integration system called Evergreen. There's separate blog posts about why we rolled our own, but we have our own continuous integration system. And so as people develop and commit changes to the server, we automatically run tests, we automatically build it and make the artifacts that go with it. And then over time, we added performance tests to that infrastructure.
So I know testing gets a lot more complicated as you scale up. I mean, in a perfect world, it's these short unit tests that all run very quick and don't do any network or anything and just kind of run them all every time. But I think that's sort of impractical as things grow and certain tests are longer or run under certain conditions or whatnot. How do you guys sort out those sorts of tricky aspects of the growth of a big project?
So on the correctness side, and I'm not the expert on the correctness side, so with a grain of salt, we run a lot of functional level tests that are really targeted at the features. And then we also run a lot of integration tests can spin up clusters with arbitrary configurations and run correctness tests against them so that we try to do a little bit of all of that. And we have some amount of randomization in the test too, with fuzzers and tests that just run for extended periods of time, trying to hit all those weird corner cases.
Well, it's very easy qualitatively to say something like we want to run a regression and make sure performance is the same as it has always been. What does that mean quantitatively? How do you measure that sort of thing?
That's a great question. And so the big change when you go from correctness tests to performance tests is you go from a binary, the test passed or failed, to a number. And so every time you run a performance test, you get a number, maybe several numbers, and you need to decide, did the performance actually change? And that's a surprisingly hard problem. We run these tests on computers, and computers are non-deterministic machines. You run something twice on it, and it's going to do something slightly different. And we also run most of our tests in the cloud. So we have virtualization in there, we have networks, we have someone else actually controlling the hardware. And so there's all this variability that sneaks in. So we've done a lot of work to control that variability as much as possible. But then even on top of that, even with things controlled as much as you can, there's still variability. And deciding if the performance changed or not has been a hard problem. We started by having humans looking at things to make decisions, and it turned out to be a little challenging to automate, which led to the paper that we're talking about.
So maybe we could describe some of those general KPIs. I suppose there's a lot of them, but something simple we could look at would be like latency or a CPU temperature or who knows what. What were you presenting to the manual inspectors when you were at that early stage of the project?
Yeah, when we started, we tried to start as simple as possible. And so the simplest tests that you can run and control for the results as much as possible are simple tests where you run a bunch of operations and you see how long it took and you compute an average throughput. So our first tests were all reporting just average throughput per test. And so it was maybe like this test got 5,000 operations per second. If it went down to 4,000 operations per second, we'd want to know. Later, we added on a lot more metrics tracking latency and latency percentiles and CPU utilizations, all those things. But that was much later on because even with simple throughputs, we were able to just overwhelm our ability to process the data.
So you were mentioning earlier about some of the non-deterministic features that could introduce noise to this process. I mean, the fact that you're on a cloud, you're at the mercy of how they distribute multi-tenancy. How noisy is this data?
It varies very much by test. So we have some tests that are really reproducible and, maybe vary a couple percent run to run. And then we have others, maybe they're more sensitive to network latency or IO latency, and those can have much larger changes, especially anything that's measuring low latencies. Things that are normally, we're measuring like a millisecond, and then it spikes to 2 milliseconds. That may not be an issue. That just may be the network. So there we could get, 50, 100% variations on some things.
Do you ever bump into cases where there's a known performance drop? Like maybe you've decided to add some highly synchronous transactional feature, and of course that'll reduce throughput, but by turning it on you get some benefit and it's a choice. Are there ever predictable declines you have to worry about like that?
Absolutely. And predictable declines and predictable improvements. So now that over the years, as we built up our system and we've gotten our developers used to it and used to the process, oftentimes we'll get a heads up before a change goes in that, hey, we expect that this will make things faster, or we expect that this will make the result slower with an explanation. And sometimes there's things that just change. Like, hey, I'm changing the test and the result is going to be different. And we track all those things, but being told ahead of time makes things a lot easier and quicker. To your original question, there's absolutely times where there are trade-offs involved. You fix a bug and things get slower, but you have correct results now. That's one we're going to accept. Sometimes you add functionality and it makes some things a little bit slower. That absolutely happens. And sometimes you make changes that will make a lot of things faster and some things slower. And we have discussions about what the right choice is there. But if it's on a positive change, we'll do that and we'll make a note of it, both for ourselves, but also so we can communicate out to the customers about what changed there.
When I think about my own experiences as a developer, which obviously is anecdotal, but anytime I ever did something that reduced performance, it wasn't really intentional. It was just, maybe I didn't think about how my code would run at really, really high velocity or something like that. It was sort of an unforeseen circumstance, or maybe I wasn't a good enough coder yet. Could be either one. What is the nature of the unexpected things you're hoping to happen? Is there kind of a pattern of developer mistakes or misunderstandings that could kind of explain some of the changes?
Oh, that's a great question. And I fear I don't have a great answer for it, but it's something that I'm very interested in. So today, we're just trying to track things and know when they changed, detect it as quickly as possible, and address it as quickly as possible, however it gets addressed. The limit of that, though, is to keep things from ever happening. And so to keep it from going in, by testing before it goes in or making sure that the developer doesn't make those changes. Now, one of the things that we've seen as we made the performance testing system better and we drove up trust in the performance testing system is the developers were more likely to test their changes using that system before their changes went in. And so there are cases where they knew ahead of time what was going to happen because they've tested it. And maybe they've kept a regression out from ever going into the system. We would love to use a lot more predictive analytics in here also. So to make that easier, we have lots of tests, and it takes a long time to run all those tests. I would love to be able to tell a developer, hey, you have your change here, run it through this system. It says you're low risk. Okay, so just go ahead. You're high risk for introducing a regression for these reasons. Maybe go check these things and run this set of performance tests to see. And I think there's a lot of things that we could do there, pulling out correlations between all of the changes going on and what's happened in the past with our performance tests.
Well, one way you could guarantee that there isn't a lot of performance change is to never update your software, which obviously doesn't make sense. But I'm curious about the volume and velocity of updates you're seeing. Is there a weekly or, some sort of sprint cadence that you keep going on? What's the release cycle look like?
So we've recently updated our release cycle. Since I've been here, we've had large annual releases. And we're still going to have the large annual releases. But starting in September, we're going to have quarterly releases that are released to Atlas, our database as a service. So we're going to get a quicker feedback there. But in general, we've been growing very quickly over the years. And so the rate of commits has been going up over the years. I actually do have some numbers. So a couple years ago, we had about 12 commits per day on average. And over 2 years, that went up to 15 commits per day. And I don't know what it is right now. I'm sure it's higher as we continue to grow the organization. So not a huge number of commits. It's not thousands per day, but it's still several and more than we can run all of our performance tests on every commit.
Sure, yeah, and certainly wouldn't scale as a manual process, as you were mentioning. Could we zoom in on that first step you took, the thresholding approach? What was the thought there?
Oh, absolutely. So when we first turned on our performance test infrastructure, it automatically ran tests, it generated results, and it graphed the results. And there weren't that many tests at the time. So we had people looking at the graphs, trying to find changes. And this is a really bad task for humans. You get bored or lose focus really, really quickly. Your eyes just glaze over. Mine may glaze over faster than others, but it's just hard. So we very early on realized that we needed a way to automate this. And so we came up with a simple system, and I think it's sort of the system used in many, many places still, which is we would compare one result to the previous result. And if it changed more than, say, 10%, we would flag it for someone to look at. We tried to be a little more clever than that. So we also checked against the last stable release to make sure that we hadn't dropped in performance, and something a week ago to make sure that there wasn't slow changes in performance coming in. And this was much, much better than having humans look at things because the computer doesn't get tired. It'll just run and do it. But it was an awful system. I think many people are still using systems like this. It's an awful system for several reasons, especially if you're running in continuous integration. So first off, different tests have different noise levels. So if you have a 5% regression, you're never going to find that if you're using a 10% threshold. Some of your tests are going to be noisier, so they're going to flag all the time. So that's depressing and hard to deal with. So it's really kind of hard to work with. We put a lot of band-aids and adjustments on it, the simple things that you could think of, but it never got easy to work with. Another reason it wasn't a good system was it also wouldn't tell us when performance changed, just that performance did change. So imagine I have a 10% threshold and the performance drops 8%. The system's not going to flag that. But imagine a week later, I have some noise and it now crosses that 10% threshold compared to my last stable release. Well, it'll flag it and a human will look at it and go, what the hell is this? And either ignore it or then spend a long time trying to trace back to find out when the performance really did change. Realize, wait, we are down 10%. Why are we down 10%? And that's one of the things that the current system does much better is find out when things change.
I would certainly want to know that as soon as possible, because if I find out later, probably other things have been built on top of that problematic commit. And it's hard to roll back or unwind all that, perhaps.
That is completely true. We've found much more so than we would have expected that the speed at which you can detect and fix something, the faster you can do that, the easier it is to fix. If you detect the thing that a developer was working on last week, they still have all the state in their head. Worst case, you can still revert that change. Best case, they know they can figure out and reason about it and make the change. If you come in a month later, all of the state is gone from the developer's head. They don't know what it is. You can't revert it because stuff's been built on top of it. And it's hard to reason about at that point.
Thanks to this week's sponsor, Quantum Metric. This is the platform digital leaders are talking about, because never before have they had such great insight into the customer digital experience. A lot of retailers do as high as 50% of their business in November and December. When you've got a hockey stick revenue time series like that, you need a tool like Quantum Metric. You don't have the time to wait for the next 2-week cycle of code releases or worse to try and get some changes out there. Quantum Metric is continuous product design. And you can get a sneak peek of how all that works by visiting quantummetric.com/podoffer. There you can see if you qualify for their 12 Days of Insights offer with code SKEPTIC. The 12 Days of Insights will give you access to the platform and deliver you a bespoke insights report that will help you identify where customers are struggling or engaging in your digital product. Some restrictions apply. Head over to quantummetric.com/podoffer and use code SKEPTIC. Seamless ML. Are you a data scientist, Kegler, physicist, mathematician who wants to be a data scientist, or quantitative researcher? Seamless ML is looking for exceptional people to join their team. The team is already stacked with one of the best poker players in Europe, one of the best cosmologists of his generation, and a top 20 Sudoku player in the world. Seamless ML is applying machine learning to do algorithmic trading. That's a challenging but incredibly rewarding project. If you're deeply committed to excellence in machine learning, this team could be the place for you to leverage your training and take the next step in your career. To learn more, head over to seamlessml.com/jobs. That's seamless, SEAMLESS, ml.com/jobs. Well, then in the same way that having a simple keyword blacklist seems like a good way to get started with spam, but doesn't get you to the final solution, thresholding seems like it made some progress, but didn't get you where you want it to be. You've kind of got the world of options, of methodologies and techniques to look at. How did you do that research process in finding out the next evolution of this project?
One of the keys was learning to ask the right question. So we realized at some point that the right question was detect when performance changes. Once you phrase the question like that, you can start asking, well, are there any known techniques for that? And heck, there's a whole branch of mathematics devoted to solving when something changes in a series of data. There's lots of algorithms, there's lots of techniques. So we started to look into those. I also got a little bit lucky in that every year we have interns at MongoDB, and we get great interns. And I had a couple of great interns. One of them went through their project really fast in the summer and was like, hey, you told me about this really cool problem you have. Can I go try it out? I'm like, sure. So I'd found some papers on time series and on change point detection, but I work in industry. I'm busy, always. So I had papers I knew I wanted to read, but they're dense and they're hard. So they sat on my desk. So my intern took the paper, read the paper, figured out that some of the fancy math on page 3 of the paper was a nested for loop, and he's skipping over the integrals on page 2. So wrote some code and did a prototype and showed that it wasn't a crazy idea. And that was enough to get us started to realize that, hey, it de-risked it just enough that we could do a larger POC and try it out. And we went through the process then of building it for real on the running system.
Were you working with the Edivisive means algorithm from the start, or did the POC involve some other change point detection algorithm?
The paper he read was the Edivisive means paper. I'd done enough reading to suspect that that was going to be a good fit for our use and likely the best of the things that I'd come across. But I hadn't actually read the paper all the way through. So he started with Edivisive means, and it's been working remarkably well for us. Do I know there's a huge number of change point detection algorithms? I don't know that Edivisive is the best out of the known ones for my use case. I know it's a good one for my use case. One of the things I've been doing is trying to leverage the academic community a little bit more, help me solve my problems. And so as we talk to people, not only share new algorithms, but give them enough tools so they can maybe go off and show us, hey, this other algorithm will be much better for you for this reason. And here's the data that backs that up.
And is there any tuning or any, hyperparameter configuration you need to worry about in rolling that out?
So for Edivisive itself, it's pretty simple. The only tuning we did, I think, was to adjust how close to the edge you can get. That's largely the main configuration you can do. You can change your stopping criterion, which is going to be based on a p-test and how many trials you run, and you can control how close to the edge that you can get. And the standard paper wanted a very large edge, and we can only run these tests so frequently, so we cut it way down for our needs so that we could signal much faster.
And could you provide a high-level summary of what the Edivisive mean algorithm does?
Yeah, at a very high level, what it does is it takes a series of data and it splits it in two. It picks a point. Well, actually, it tests this for every point, but it picks a point, and for each point, it calculates a few numbers. It calculates a number based on all the numbers on the left half of the series, a number on the right half, about how similar those numbers are. And then it computes that same number, how similar are all the points across the whole series. And what it's going to look for then is a large difference between how similar all the points are in the series to how similar the points on the left are to the points on the left, and how similar the points on the right are to the points on the right. And so as it goes through, it'll find the point, the pivot, if you will, the split between left and right that gives the largest difference. And I'll label that as the most significant change point. And that's what it's doing to find changes.
I think you'd mentioned that the intern determined this was a nested for loop. Does that present any computational challenges? Is this expensive to run?
So we were worried about that. Our first implementation was n cubed, a very naive algorithm. We're able to get the nested for loops down to n squared, and it hasn't been a problem. Our data just hasn't gotten large enough for that n squared to really be a problem. And we've optimized the algorithm so it's pretty fast. At some point, the n squared will be a problem, and it'll be trivial to take care of because we'll just truncate the data at that point. If it can handle a year's worth of data already, I really don't need 2 years. I can just say, okay, just find me the changes in the last year, and that'll be fine.
Yeah, 2 years ago are probably hardly representative of modern performance metrics at the rate you're merging changes.
Exactly.
Well, I'm curious, I know the manual process won't scale, but I'm always kind of reminded of Andrew Ng's 1 second rule, where he says, if you can look at something like an image and in 1 second make the classification, almost certainly machine learning can do that for you. Do you find that these plots have the same characteristics, that these change points are rather obvious, or is it a bit tricky to find some of them?
So some of them are obvious and some are a lot trickier. I have an example or two in the paper with changes where the signal to start with, the series, was a little bit noisy. And then you have a change that's on, say, the magnitude of the noise, of the variability before. And so it'll take more than a second, I think, to look at those and figure out where things changed. And the algorithm's actually really good at finding those. It'll even find things where there's nominally no change in performance, but the test got noisier for some reason, or less noisy, because the distribution has changed, which is also interesting because I want to know if the test gets noisy.
Do you have a sense of your false positive rate in this process?
It's sensitive to how you calculate it. So going from the threshold-based system to the change point detection dropped our false positives by at least an order of magnitude, if not more. It was drastically better. But we still have more, I'm not sure I even want to call it false positives. We still flag more things than we want to look at. And I use those words carefully because there's a lot of reasons why performance can change, and there's a lot of amounts. And so if performance changes 1% on a noisy test, and my algorithm can tell me it changed 1% on a noisy test, well, I guess I'm glad to know that, but I don't think there's anything I can do about that. I mean, I just imagine handing that test to a developer and say, go profile this and figure out where this 1% came from. Oh, and you might have to run it 1,000 times in order to see that. But there's also things where the performance changes because of things we can't control. We've had cases, these are the really nasty ones. If any of your listeners have ideas, I'm all ears. But we have cases of correlated noise. And so an example of this would be things that are related to the compiler. When you compile the code, you get a certain code layout, and that code layout fits in caches a certain way. And so we'll see some of our more sensitive, really micro benchmark kind of tests that are really focused on a particular feature, where they'll go from fitting efficiently in a particular cache to not fitting efficiently in that cache. And we'll get a change, and it'll be a clear change. You look at the graph, your eyes will go, there's a change there. And it's a reproducible change. If I recompile it and run it again, I'll get the same answer. But there's nothing any of us can do about it, or I haven't figured out what to do about it. Again, if anyone has ideas outside of using 5 different compilers, and actually we looked at that, but it's telling us things that might be real about the system that we're not interested in, and trying to get to bubble to the top the things that are useful information and actionable information are the hard parts in there. And so we're continually trying to improve that.
Yeah, makes sense. And as a developer, I don't want to have to worry about the compiler at all.
I mean, that was a really nasty one when we finally figured out what was going on. We profiled it. The profiles were identical. We had to go with performance counters. And the only thing that differed on the first point was the cycles per instruction.
Well, I'm curious, we've talked a little bit about the false positives. Do you have a sense of any false negatives? Are there things like memory leaks that only occur slowly over time that are hard to find?
There's 2 things worth talking about on the false negative side. First is just coverage. We sell a general purpose database that people can use in an infinite number of ways. And so my biggest concern on that front is having enough representative coverage that if the performance changes in a meaningful way for a customer or for any user, that we can detect that ahead of time. That's a challenge that takes a lot of thought and energy. The second one is the small changes. And I used to believe that these didn't exist, which was small, say 1% changes that add up over time. And for a long time, we just would not see any of those. And now in the last year, we've seen a couple, and we're trying to figure out how to deal with it. But for the most part, I think we are catching all of the performance changes that for things we're measuring. Lots of things that we're not measuring that we would like to, but for the things that we're measuring, we're catching them. And I know this because we don't just trust the computers. One of the things we have is we go through routinely, like once a month, and look through all the data to make sure that everything has been processed properly. We have an algorithm that detects change points. We have humans that process the change points. We have developers that then fix things. We have this monthly checkpoint to make sure that each stage of that is working properly and that we haven't missed things. And we will find cases where there was something detected, but it didn't make it all the way through the pipeline. And we'll catch it at that point. And then we ask, why didn't we catch it and what can we do better? There's very infrequently where we catch something where we have, well, yes, we have a real 10% change in performance where there isn't underlying change points that we can find when we go back and look again for them.
Is there anything unique about this project that it's specific to MongoDB, or might these approaches generalize to other software projects?
The infrastructure to run the tests is fairly specific to MongoDB. I think the performance analysis side of it is completely generic and relevant to anyone testing performance over time. Testing performance in a controlled way over time. And in fact, one of the things we've done in the last year that I'm quite excited about is we've worked with an organization, SpecRG, with a few other organizations which have the same problem. And we're working together to try to share data and to solve common problems. Coming together with multiple data sets, we can then share and let academics work on real-world problems and solve all of our problems together.
Absolutely, yeah, and maybe those compiler authors can learn something along the way too. Well, what's the horizon for this project? Is it pretty much mature and just running, or is there ongoing work?
There's two parts of it. One, it's ongoing with lots of work going on, lots of discussions. And so I'm very optimistic about it. And, if other people want to join in, more data is always better. I suspect that comes up with the data science stuff, doesn't it? In the shorter term, with our data ourselves, we have made recently an artifact with all of our performance results, all of our performance test results for the last few years, and put it up on the web on Zenodo. And we're running a data challenge based on that data. So there's a computing performance conference called ICPE. And next year, there's a data challenge with that. So people can take our data, do something interesting with it, write a paper, and submit it to the conference for that track. And I'm really looking forward to see all of the cool and interesting things people do with our data.
David, where can people follow you online?
I have a website, daviddaly.me, and I'm on Twitter at daviddaly44, talking about performance stuff.
Very cool. Well, I'll have links to both in the show notes so people can follow up.
Excellent.
Thank you so much for taking the time to come on today and share this work.
All right. Thanks for having me.
That concludes another installment of Data Skeptic Time series. Our guest today, David Daly. Thanks to our sponsors, Quantum Metric and Seamless ML. Myself, Claudia Armbruster, as associate producer, Vanessa Bly, guest coordinator, and our host, Kyle Polich.